Good day, everyone. So we are reviewing Wetzel's Limnology textbook. This is edition number 4, which was published in 2024. And today we'll be starting chapter 8, which is about 45 pages. So it's going to take us a little while, probably about 8 days to go over this chapter. And it focuses on water movements. And it was put together by David P. Hamilton with the Australian Rivers Institute in Brisbane, Australia, and Sally McIntyre with the University of California, Santa Barbara. And so why don't we jump right in? Lakes, ponds, reservoirs, and flowing waters are dynamic systems in which organisms live, grow, and actively move or are passively transported, and where a diverse set of biogeochemical reactions occur. The movement of water within these aquatic ecosystems influences how organisms are distributed and where, when, and how fast reactions occur. Through theory and experimentation, both in the laboratory and in the field, the mechanisms influencing the flow of water have been identified and evaluated. Hydrodynamic modeling has extended our understanding of the individual processes at scales up to the whole lake or whole river. In this chapter, we cover pertinent physical processes, in particular turbulence and its influence on dispersion and mixing over large and small scales. Turbulence is enhanced in boundary layers, such as the surface of lakes and rivers, directly influenced by the atmosphere, and the bottoms and sides of lakes and rivers where currents interact with the substrates. Wind, cooling of surface waters, and the flow of water generate large-scale flows, such as currents organized spiral motions called Langmuir cells. Surface waves, flows driven by differences in density and internal waves. Curvature in streams and rivers, and variability in lake morphometry and the wind field induce spiraling motions in streams and gyres in lakes. We describe these processes and provide equations pertinent to quantifying the flows and mixing. On the system scale, flows interact with boundaries and density stratifications, and the magnitudes of currents and turbulent mixing changes. We provide examples of the resulting spatial and temporal variability of physical perturbations and their importance for ecosystem processes. Similarly, we review 1- and 3-dimensional hydrodynamic models and provide examples of how they can be used for predictions of changes in the hydrodynamics of lakes over time and in ecosystem studies. Hydrodynamics and physical limnology. The flow of water within streams, rivers, lakes, ponds, and other water bodies is governed by principles from the field of hydrodynamics. The ensuing motions determine the habitats for aquatic organisms and create conditions that influence biogeochemical reactions. Hydrodynamics deals with the movement of parcels of water, each containing a large number of molecules, not the movement of individual molecules. Understanding hydrodynamics requires considerations of the properties of water and ice, including density, specific latent heat, and specific heat capacity, viscosity, and molecular diffusivity, the forces acting on the water, and the ensuing response. In aquatic systems, water motion is induced by gravity, as in streams flowing downhill, by wind that induces currents, and by uneven heating or cooling, which causes density differences that drive flows. Water motion is also influenced by short-wave and long-wave radiation, evaporation, and conduction, which influence density stratification. The presence of boundaries modifies flow. For example, in streams and rivers, friction slows currents near the bottom. The curves in streams and rivers create eddies and meanders, and the friction from wind acting on the surface of the water creates currents. The regions in which the flow is modified are called boundary layers. As the flow of water modifies the habitat of organisms and transports solutes critical for the growth of organisms or pollutants that are detrimental, a key goal in physical limnology is to quantify advection, how fast water flows, dispersion, by turbulent motions, how fast it spreads, and mixing, how fast it homogenizes by spreading and diffusion. Quantifying advection, dispersion, and mixing relies on conservation laws for mass, momentum, and energy that are used in mathematical formulations to determine the velocities, pressures, and temperatures of water. These formulations are the basis of hydrodynamic models used to simulate the dispersion of heat and solutes, as well as the foundation for water quality models that describes the way in which planktonic organisms, solutes, and particulate materials are redistributed by water movements. Theoretical, laboratory, and observational studies have been essential for identifying critical hydrodynamic processes. Both measurements in the field enabled by recent advances in sensor technology and hydrodynamic models have greatly extended theoretical and laboratory studies by providing assessments of mixing dynamics in inland water bodies, by identifying flow patterns, and by quantifying the resulting advection, dispersion, and mixing. The fluxes due to turbulence, that is spreading and mixing, are quantified using coefficients of dispersion and eddy diffusivity, and for wind speed less than 10 meters per second, gas transfer velocities. Understanding these topics is essential for describing how physical processes moderate ecosystem functions such as metabolism, and for calculating the fluxes of climate-forcing trace gases. Laminar, transitional, and turbulent flows. Water in lakes and rivers is not still, with its motion categorized as laminar, turbulent, or transitional between the two. Laminar flow is characterized by linear motions, and transitional flow is characterized by distinctive curving motions, while turbulent flow is denoted by irregular, chaotic fluctuations in velocity and pressure that generate mixing. The types of flows that occur in a system can be predicted by dimensionless indices. These indices are developed by considering the forces acting on a parcel of water or a water body, evaluating the dimensions, and collapsing the terms. Dimensionless indices commonly used in studies of inland waters to understand turbulent flows are the Reynolds, Richardson, and Froude numbers, and the Wedderburn and related lake numbers. Other metrics describe the dominant forcing mechanisms. For instance, the Monin-Obukhov length scale indicates the depth to which turbulence production from wind-induced shear exceeds turbulence production by near-surface cooling, and the Dam-Kohler number is used, for example, to infer whether there is adequate time for a chemical reaction to occur prior to flow out of a system. The Reynolds number, Re, is the ratio of the inertial force of the water to its viscous force, where U is the mean velocity of the fluid, meter per second, L is a characteristic length scale, like meter, and omega is the kinematic viscosity of water, 10 to the minus 6 meters squared per second. Re is equal to minus UL over, V or omega here. The inertial forces, F1s, are derived from Newton's second law of motion. F1 is equal to rho AU square, where rho is the density, A is the surface area, and the viscous forces FV are given by FV is equal to mu over AU divided by L, where mu is is dynamic viscosity, a measure of the stickiness of the fluid, or strictly the resistance to deformation. For this case, L is a length scale with S is equal to L squared. The ratio of the terms is equal to F1 is F1 divided by FV is equal to rho LU divided by micron. In the Reynolds number, micron divided by rho is kinematic viscosity as used in equation 8-1, and conveniently is nearly constant. So in water. So let's see here, figure 8-1. So laminar flow. So this is laminar flow here. This is transitional flow. So it's between laminar and turbulent. This is turbulent flow. And then D is, let's see here, turbulent eddies in a flow. The stretching of the fluid by the larger eddies creates smaller ones, and these in turn become smaller, and gradients become progressively thinner, such that final mixing, not shown, is by molecular diffusion. When inertial forces dominate, the fluid will tend to stay in motion once in motion. When viscous forces dominate, the motion will tend to cease due to friction. The transition between laminar and turbulent flow varies depending on scale and application, but within aquatic ecosystems, turbulent flows are prevalent. For calculating RE in a stream, L is equivalent to the hydraulic radius RH, defined by the area of the cross-section of the stream channel divided by its wetted perimeter. In lakes, L can be the depth of the upper mixed layer. When calculated using conservative velocities in the upper mixed layer of a lake, for example, 0.01 meters per second, and a mixed layer of, say, 4 meters, RE is equal to 40,000, indicating turbulent flow. However, the upper mixed layer is often stratified for part of the day, so for addressing whether the flow will become turbulent in the presence of vertical density gradients, dimensionless indices such as the Richardson number are used. Considerable experimentation has been done to find the transitional values of Reynolds numbers for different types of flows. These include experiments with flow over flat plates, analogous to the flow over the surface of a lake, flow around cylinders, which is analogous to flow around stems, in beds of aquatic macrophytes, and flow due to plumes descending from the surface of a lake as it cools. A basic use is for flow around organisms, in which case the transitional value is approximately 1. Thus, for larger organisms that swim quickly, such as fish and large zooplankton, inertial forces govern their world. In contrast, for small planktonic organisms, RE less than 1, and viscosity dominates, and adaptation are required for locomotion. Hence, in evaluating whether flow is laminar or turbulent, it is critical to consider the application. The Richardson number, Ri, is used to determine whether a stratified flow is turbulent. Stratification is considered stable when less dense water overlays denser fluid. These conditions occurs in freshwater when warm water overlays cooler water at temperatures above 4 degrees C, and the converse occurs at temperatures below 4 degrees C. Ri is the ratio of the buoyancy forces due to stratification that resist mixing to the initial ones that induce it. So Ri is equal to this set of expressions, and where G is the gravity, rho is the density, Z is the depth, d rho over dz is the change in density with depth, and du dz is the change in horizontal velocity with depth. The equation can be written as Ri is equal to n squared divided by s squared, where n is the buoyancy frequency, also known as the Brunt-Wetzel frequency, and it's per second, and s is per second is the vertical shear of the horizontal velocity, du over dz. In this form, Ri is called the gradient Richardson number. For Ri less than 0.25, flow can become unstable, such as denser water overlays less dense water, resulting in mixing. Kelvin's Helmholtz billows form as the flow becomes unstable. In lakes, the vertical dimension often depends on the degree of stratification, with overturns of 0.25 meters vertical scale at times in the metalimnion. So let's look at this here, figure 8-2, growth of shear instability leading to turbulent mixing in a stratified fluid with velocity, U and density rho, profiles with respect to depth Z, shown in A, and initial stable stratification with less dense water white over denser water black, and flow a direction indicated by arrows in B. Okay. A and B are fixed points, and the lines represent surfaces of equal density. As flow begins, the motion becomes wave-like, C and D. Okay, right here. The wave-like features become unstable and in E and F, so instability in E and F, and further roll into Kelvin-Helmholtz instability G, and before collapsing in a turbulent patch H. With I and J illustrating the final stages of mixing in which the fluid is nearly homogeneous. So here we have nearly homogeneous fluid, and this is the fate of the point A and B here, which we find right here in a laminar type of flow. So this pretty much is an evolution from laminar flow to turbulent flow through the phase that is we call it, let's see here, this phase here, which is transitional phase. Okay. Over terms such as the Kelvin-Helmholtz billows become turbulent eddies, illustrated that overturn can be identified with high-resolution temperature sensors, and that they occur more frequently in the upper mix layer than in the thermocline. These observations provide a framework for many subsequent studies of turbulence. The overturning regions are called Thorpe scales, and turbulent length scales are often assessed by determining the size and frequency of the Thorpe scales. Turbulence and the energy cascades. Turbulent eddies cover a range of sizes. For instance, they can be as large as the depth of the upper mix layer, which can range from 50 to 100 meters, or a meter or less, depending on lake size, magnitude of prevailing winds, heat loss at night, and clarity, as well as the width and depth of the channel. In stratified flows, as in the thermocline of lakes, the largest size may be that of a Kelvin-Helmholtz billow, and considerably smaller than in the mixed layer, due to stretching, folding, and vorticity, that is, spinning induced by velocity gradients. The largest eddies spawn progressively smaller ones down to the scale of viscosity. This process was penned as a poem by L.F. Richardson. Big whirls have little whirls that feed on their velocity. Little whirls have lesser whirls, and so on to viscosity in the molecular sense. Eddies can be described as a rotating region of a fluid. They can also be characterized by turbulent velocity fluctuation, U, with a certain length scale, L. This approach enables a turbulent flow field to be envisioned as covering a spectrum of wavelengths, each of which applies to the diameter of an eddy. The larger eddies obtain their energy from the forces generating turbulence, that is, wind, cooling, or gravity, also known as the stirring agent. At the larger scale, the turbulent velocity fluctuation may not be the same as in the horizontal and vertical, indicating that the turbulence is anisotropic. So let's look at figure 8-3 here. Kelvin-Helmholtz billows with an upper layer that is slightly less dense and flowing faster than the fluid below. The fluid movement progresses from waves in the upper panel, so waves here, so we have less dense over denser, from waves to billows, middle panel, and is beginning to collapse into turbulent motion, lower panels. The photographs are from a laboratory experiment in which fluorescent dye dissolved in the lower layer is illuminated by a thin sheet of light. 8-4. Example of turbulent eddies and gyres, a rotating transitional flow, acting at two different scales to disperse and concentrate cyanobacteria at the water surface of Lake Ohinewai, Waikato in New Zealand, and Lake Erie in the US. So here we have both turbulent and transitional flow. So if we look at, so this is at the macro scale here. This is turbulent flow. This is, I believe, a satellite picture of Lake Erie. And so we have turbulent flow here, and then we have transitional right here, as well as here. Although that's probably unclear. It's probably potentially actually turbulent here. If we look at the example that they gave us in terms of, so this is laminar, transitional, and turbulent. So there's still some organization at the transitional level. So in terms of any like flows that seem to be organized to a certain extent before becoming completely turbulent, I would say that this looks pretty organized still, and this does not look organized. Okay. So the energy cascades to eddies of moderate scale in which the turbulence is isotropic, that is, the magnitude of velocity fluctuation is the same in all directions. Here, the energy cascades as a function of the wave number, the inverse of the wavelength, in a predictable manner, and eddies in this size range are classified as being in the inertial subrange. The smallest eddies are classified as being in the inertial viscous subrange, where some dissipation of energy by viscosity occurs, and finally in the molecular subrange, the energy of turbulence is transferred to heat. The concepts related to the size and velocity of turbulent eddies led to what is called the statistical theory of turbulence. Spreading and mixing are conceptualized as the product of the turbulent velocity u and length scales, that is, coefficient k, describing turbulent diffusion units of meter square per second, can be written as k is equal to C1 UL, where C1 is an empirically determined coefficient. The large scale eddies are related to the smaller scales through the rate of dissipation of turbulent kinetic energy, sigma, that is the rate that energy is lost from the turbulent motion by viscosity unit of meter square per second to the third cube. So that indicates an acceleration. These relations, experimentally verified as will be seen below, have been critical for understanding hydrodynamic processes and their biogeochemical implication in aquatic systems. Measurements of turbulence require instruments capable of sampling fast enough to capture the turbulent velocity fluctuations or the fluctuation of scalars in the flow, such as the temperature. So why don't we stop right here, and we'll continue tomorrow to go over the continued content here. Well, maybe I guess I could just push it on to boundary layers. These data enable the quantification of the turbulent kinetic energy of the flow, its production, transport, and decay. This later quantity is the rate of dissipation of turbulent kinetic energy, is the most commonly measured of these terms. With it, the turbulence within the mixed layer, thermocline, and hypolimnia of lakes have been described, as well as flows in the rivers. Temperature sensors with sufficient resolution can be used to identify turbulent length scales, that is, instabilities such as those from Kelvin-Helmholtz billows or near-surface cooling, which lead to penetrative convection. Additionally, sigma enables a description of the smallest scales of turbulent flow with application to the environment of phytoplankton and other microbes, as well as the fluxes of dissolved gases.